In this lesson, I will explain to you the concept of hill climbing algorithm in artificial intelligence. As we had discussed in our last lesson in beam search algorithm, that the value of beam may be 2, 3, 4, and so on. But what happens if the value of beam is 1? When the value of beam is 1, we have to use hill climbing algorithm. Now, what is the meaning of beam is equal to 1? Sometimes in different books, you can see instead of beta, they are using n. Sometimes they are using m, but the concept is same. It means the beam width. They are talking about the beam width, and in hill climbing algorithm, the beam width is always 1. So here I have written some information regarding hill climbing algorithm is a local search algorithm that it knows only about the local values. It does not have the knowledge of global domain, which continuously moves in the direction of increasing elevation value to find the peak of the mountain. As the name indicates, hill, right? So I will explain to you by using the same example, the word they are using, mountain, or best solution to the problem. It terminates when it reaches a peak value where no neighbor has a higher value. Its beam width value is equal to 1. This is the important point. And the most important point is we have to use this when we will make our decision. If the new state is better than the current state, then it is considered new current state. Otherwise, it stops. Right now, what is the meaning of this? See here, this is our starting point, and this is suppose our goal state. We have to start from here and we have to end our journey here. Suppose the heuristic value, the estimated value, again it follows the greedy best way. Greedy means if the heuristic value is low, we have to follow that path or that route. It always use the best move, right? What is the meaning of best move? And the other important thing is that here in this hill climbing algorithm there is no back track. If the dead end will come, we cannot go back. So this is our starting point and the heuristic value is 20, suppose. Now we will say that from this S we have three different routes which will take us to our G, A, B, C. Suppose these are the routes, and the heuristic value, suppose A is 19, heuristic value of C is suppose 18, and the heuristic value of B is 17. As we know here that our beam width is 1, it means we have to explore that node which has the lowest heuristic value. So in these cases, we have here 19, 17, and 18. It means this is the lowest. So we will explore B. We will not keep A or C in our memory. If something will happen, if we will find the dead end, we cannot track back and we cannot go to these routes in hill climbing. Only we have to follow one route, the best move we have to take. So this is the best among these three. But again, one important thing according to this sentence, see here the heuristic value is 20, this heuristic value is 17. It means this one is better than this. That is why we are taking this. If all the heuristic values here will be more than 20, we will not explore either node from here, right? So if the new state is better than the current state, this is our current state, this is our new state. If our new state is better than the current state, then it is considered new state and we will explore. Otherwise it stops. So it means we will explore here, and these two we will not keep in our memory, only this one, right? So here from B, suppose we have one D, E, and F. We have three different routes. B, right? And if the heuristic value, suppose D is 16, this is 15, this is 14. So which one is best? Which is the lowest move, lowest heuristic value? F. It means we have to explore F. We will not keep this in our memory. We will not keep this in our memory, right? In this way, our space complexity will be low because we are following only one best route. And you can see here again, according to this sentence, see here, this is 14, it is better than 17. If it is will be 18, then we will not accept this, right? So this is better than this. It means that we have to follow now this route in order to reach here. Here and here, suppose we have two, this is H, this is I, and the heuristic value is, suppose here, now this is 20 and this is 20. Both are same, right? Both are same, but these heuristic values are not better than this. This one is our current state now. This one is our current state. We have to compare the heuristic value with this now. So if it is even 15, 16, 17, whatever, it is not better than F. And it says if the new state is better than the current state, these are the new state, both are same, even if they are different, 19 or 20, we can stop here. We cannot explore this or this either, because both moves are not best according to F, because here is 14, it should be less than 14 in order to reach here, and there is no backtrack, so we can stop here. This is the hill climbing. And see here, in case of this hill climbing, every time you are taking the best move, best move, best move, right? Best, this is suppose 14 and 17, best move. If some we have some obstacles, we can not take that path here, 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 and we will come at the point where we will stable, right? It means that this is the maximum value or stable value we have reached here, this point. But when we see here that we have another mountain, another hill is here, actually we have to go there, as it's mentioned here that this is the local search. Only we know that here, if we are here, we know that we have to reach here. When we come here, we find out, oh no, we have to reach there. But according to hill climbing, we cannot go down. No, this is the maxima, right? So here we have some problems in this algorithm. So what are the problems? These are the problems: local maximum, plateau or flat maximum, ridge. Now what is the meaning of these three? We will discuss. First we will discuss the local maxima. For local maxima, I have made this and this for you. Same thing here, we are taking the best move, best move, best move, right? Suppose the heuristic value of our first step is 20, second will be 19, then 18, and so on. If it's the best move less than the previous, yes, we are going, and we reached here. This is the local maxima because we have the local information only. But when I reached here, we have figured out, oh, there is another hill, we have to go there actually. But according to this, we cannot go down. Right here, if we will go there, it means we are coming back to our lowest point. So this is the local minima, right? Local maxima, local minima. This theorem not allows us to go to the local minima. So we have to stop here. This is the global maxima, right? Global minima, and here, because this theorem follows the local search, that is why we have to stop here. Second one is the flat maximum or plateau. Now what is the meaning of it? Same thing, just take the example of our starting point, and then we have three different routes here, A, B, C, and here is, suppose this is 20 heuristic value, again this is 18, and this is 17. It means we have to explore this. We will not take this our memory, we will not keep these two in our memory. When we will explore this, right, and it is better than this because this step is 17 and this is 20, it is better. Now here, suppose C has three different routes, maybe G, H, and I, and all have the same values, same heuristic values in order to reach our goal state. Now, which one you have to take? So, if we have the same, it means we have to stop here. This theorem says that if all the heuristic values are same at any point, we have to stop here. We will not explore any other one. So this is the flat maximum. This is our best move. This is our best move, right? C, best move. After that, it is flat. All are same. It means we have to stop here. So these are the problems, drawbacks of this theorem. And the final is the ridge. What is the meaning of ridge? This is the example of ridge, but I can make one more example here. If I will make just 3D, this is my C point, this is my D point, right? This is all the best moves we are climbing. When I reached here, we notice, oh, there is another destination. But see, this destination in the direction is this. It does not allow us to change the direction either. So we cannot change the direction. We have to stop here, right? So this is all about hill climbing algorithm. Again, the beam value is 1. Whenever is the beam value is 1, you have to use hill climbing method. If the beam value is 2, 3, and so on, we will use beam algorithm. So please practice it, subscribe to my channel, and thanks for watching.